Object detection from images using convolutional neural network based on deep learning. Abstract. According to the object detection definition, object detection can be defined by identifying different objects automatically from image files. Implementing by multiple deep learning technique, many problems which occur frequently and disturb the accuracy can be improved. Convolutional neural network are currently the state-of-the-art solution for object detection. To improve and test object detection system is the main task of this project. This system is applied for images based on convocational neural network. In this arena there are two parts. From theoretical part, relevant literature, and how convocational neural network improved computer vision are studied, and from the experimental part, how easily a convocational neural network can be implemented for object detection will be shown. Keyword: convocational neural network, deep learning, CIFAR 10, dataset description, object detection. Introduction. There is a huge amount of image data in the world, and the rate of growth itself is increasing. Before around 2012, a dataset was considered relatively large if it contained 100 plus images or videos. Now, datasets exist with numbers ranging in the millions. Many of these images are stored in cloud services or published on the internet. Over 1.8 billion images were uploaded daily to the most popular platforms, such as Instagram and Facebook. We need to have some effective ideas about its contents to manage all of this data too. Automated processing of image contents is useful for a wide variety of image-related tasks. For computer systems, this means crossing the so-called semantic gap between the pixel-level information stored in the image and the human understanding of the same images. Computer vision attempts to bridge this gap. 3. Object detection from repository of images is challenging task in the area of computer vision. Lately, a lot of work has been employed in the object detection. CNNs have a high computational cost in terms of memory and speed in the learning stage, but can achieve some degree of shift and deformation invariance. 5. Nowadays, this approach became more feasible thanks to the hardware evolution and the capable of using the GPU processors to perform convolutions and the large amount of available data that allows the learning of all CNN's parameters. 13. This network type has demonstrated being able to achieve high recognition rates in various image recognition tasks like character recognition, handwritten digit recognition, object detection, and facial expression recognition. 6. Although there are many methods in the literature, some aspects still deserve attention. For example, accuracy is somewhat low and validation methods could be improved and the recognition time could be a little improved to be performing in general. 8. 3. Methodology. Backpropagation is defined by the way the computer is able to adjust its filter values, or weights, by applying a filter process. Among different ways, a common loss function is MSE, mean squared error, which means 1/2 times, actual predicted, squared. Equals 0.12, 2. Where L equals total error. AP equals target probability. YP equals outcome probability. For reducing loss, the main task is trying to adjust the weights. If the loss is increasing, the derivative of the loss with respect to the weight will be computed. DL/dW is the mathematical equivalent of this, where W are the weights at a particular layer. Now the process of loss decreasing is applying by the backward pass through the network, which determines which weights contribute most of the losses and then finding ways to adjust them. After completing the computation of the derivative, the last step called weight update can be moved by us. Not only this, but also for changing the gradient in the opposite direction, all the weights of the filter are taken and updated. Equals, dash. Where W equals weight. WI equals initial weight. Equals learning rate. One of the parameter is learning rate that is chosen by the programmer. When bigger steps are taken in the weight update, it is called high learning rate. As a result, for making the model to converge on an optimal set of weights, it may take less time. Moreover, jumping can be the result where the learning rate is too high and large and not explicit enough to reach the optimal point. 10. The overall training process of CNN can be summarized as below. Step in the training process of CNN. Step 1. Initialize all filters and parameters/weights with random values. Step 2. The network takes the training images as input, goes through the forward propagation step, convolution, ReLU, and pooling operations along with forward propagation in the fully connected layer, and finds the output probabilities for each class. Step 3. Calculate the total error at the output layer. Total error equals 1/2, target probability output probability, 2. Step 4. Use backpropagation to calculate the gradients of the error with respect to all weights in the network and use gradient descent to update all filter values/weights and parameter values to minimize the output error. Step 5. Repeat steps 2 to 4 with all images in the training set. 4. Model design and implementation. In this method, CIFAR 10 dataset is trained by us, through using convolutional neural network. 10 unique data classes are contained by CIFAR 10 dataset. That is why this model is trained only for these 10 objects. The dimension of the image of our dataset is 32*32. For extracting data from input and fitting the model, different convolution layers are used. Dataset description. For training the model, CIFAR 10 dataset is used by me, which contains 32 times 32 color images in 10 classes, where per class have 6,000 images. As a result, in total it has 60,000 images. Not only is this, but also there are 50,000 training images and 1,000 test images. 5 training batches are the divisions of the dataset, where each batch contains 10,000 images. Here, exactly 1,000 randomly selected images are contained by the test batch and the remaining images are contained by the training batches in random order. Capture.png. Figure 2, CIFAR 10 dataset. The one more thing here is that more images from one class than another can be contained by some training batches. But among them exactly 5,000 images are contained by the training batch from each class. The network. Deep CNN with 4 convolution layers and 2 fully connected layers are trained. The first convolution layer had 32 iters, the second one had 64 16 iters, and the last one had 128 iters. Layer, type. Output shape. Table -1, different layer and their dimensions used on this project. From the entire convolution layers, we have a stride of size 1, batch normalization, dropout, max pooling and ReLU as the activation function. 80 neurons are contained by the hidden layer in the first FC layer. Batch normalization, dropout, and ReLU are also used in FC layer which are also similar in the CN layers. Additionally we also used softmax as our loss function. Table 1 shows the architecture of this deep network. Results. To show the performance of the deep CNN model, we plotted the loss history and the obtained accuracy for the model. Figures 3 and 4 exhibit the results. As seen in figure 3, the deep network validation accuracy is 84.89%. Accuracy.png. Figure 3, accuracy of training and validation dataset. Loss.png. Figure 4, loss history of training and validation dataset. L&A.png. Figure 5, training loss and accuracy on dataset. Confusion matrix. A confusion matrix is a table that is often used to describe the performance of a classification model, or classifier, on a set of test data for which the true values are known. The confusion matrix itself is relatively simple to understand, but the related terminology can be confusing. We computed the confusion matrices for our deep CNN. Table 2 presents the visualization of the confusion matrices. As demonstrated, the deep network results in higher true predictions for most of the labels. Table 2, confusion matrix for object detection system. 6. Conclusion. From the above description both in experimental and theoretical experiences are revealed about the development of an object detection system. The most precious matter is that GPU has shown better performances by applying deep convolution network trained on it except the higher cost factor of it. Learning rate, the number of layers, the type of each layer, the area size of convolution and pooling and so on hyperparameters are optimized by the deep architecture. On the other sides, grid search and manual search are used for hyperparameter optimization. Furthermore, for ensuring the main motive of object detection above model can also be utilized. 7. Future work. In the future work, we would like to plan to use more advanced network that will be helpful to train deep architectures and allow us to investigate the accuracy of our object detection system. Image localization was left outside the scope of the project due to not having GPU.